It's Paul with the very last of the Math 156 videos, this one on using bootstrapping and part of the student T idea to generate confidence intervals that work even for wildly skewed distributions. This is based on example 7.21 in the textbook, and you'll probably want to stop the video and go and read that section of the textbook if you haven't already done so. Welcome back. The subject is arsenic in wells in Bangladesh, which is one of our standard examples of a distribution that is wildly skewed to the right. There are a small number of wells that have enormous concentrations of arsenic in them. So we'll load the data, and we only want to work with the arsenic. Let's plot a histogram, and you can see there's at least one sample is way off the charts, greater than 2,000 there. The mean, on the other hand, is only 125. We can compute the sample standard deviation, and we can divide by the square root of the number of measurements to get the standard error. However, when people see standard deviations and standard error, they tend to jump to the conclusion that the data are normally distributed. That's not the case at all here. Nonetheless, we can deal with this by doing a bootstrap. So let's first check out our methodology. How do we bootstrap? We draw a sample of the same size n by sampling with replacement from the data that we've got. So that means we'll use some wells multiple times, some not at all. And then we will compute something that is in the spirit of student T. We will take the mean minus the sample mean, and we will divide by the standard error, the standard deviation, over the square root. This is a so-called T statistic. Now let's try to estimate the distribution of this. You say, what do you mean estimate it? It's got a student T distribution. Oh, no, it doesn't. If our original data were drawn from a normal distribution, this would have a student T distribution, but we weren't drawing samples from a normal distribution at all. So let's figure it out. 10,000 times, we will draw a bootstrap sample, compute this T star, student T-type statistic, store the means, store the standard error, and now let's think about what we've got. Remember that in the derivation of the student T distribution, we had to assume that the standard error was independent of the sample mean, and we were able to prove this only in the very simple case of drawing two samples from a normal distribution. But it turns out that in general, this independence assumption is only valid for normal distributions, which we haven't got here. And in fact, if we plot the means and the standard errors, we see that they're highly correlated. A large mean is correlated with a large standard error. We can actually ask for the correlation, 88%. With a normal distribution, we'd expect to get something close to 0. And that means that our bootstrap T statistic doesn't resemble either a normal distribution or a student T distribution. We can check that by looking at the distribution of T star and comparing it using QQ norm. In case you didn't believe that that's not a straight line, here's QQ line to show that it isn't. Interestingly, this bootstrap T statistic is skewed to the left, not to the right. Here's a histogram of it. You can see it is indeed skewed. If we were foolish enough to assume that this distribution was student T, we'd be way off. The student T distribution with the same number of degrees of freedom matches the mean, matches the standard deviation, but doesn't match the shape. And you'll recall that's generally true of bootstrapping. that when you do a bootstrap, you're stuck with the mean and standard deviation of your sample, but you can pull out information about further details of the distribution by bootstrapping that go beyond that. Now we'll get our quantiles. The quantile function takes this vector t star and pulls out the 2.5% and 97.5% quantiles. If you compare with the book, you'll discover the numbers aren't quite the same. Why are they different? Because the book drew some bootstrap samples, we drew some bootstrap samples, but we got a different set of samples from the book and we got some different numbers. Okay, we'll pull out the quantiles. There they are. And now we're going to use the usual technique. To get the lower endpoint of our quantile, we will use the observed 97.5% quantile, the upper quantile, obtained from our bootstrap distribution. We'll multiply that as usual by the standard error. So we'll get an L that is less than the sample mean. We will get a U that's greater than the sample mean. And we say we're 95% confident that the actual concentration has a mean that's in between 95 and 174. Previously, we used the Bootstrap percentile confidence interval. That gives quite different numbers, and the Bootstrap percentile confidence interval does give you an interval which has the probability of 95% that the true value lies in the confidence interval, but you make errors a different fraction of the time on either side of that. So this new way of computing a Bootstrap T confidence interval is, in my opinion, greatly superior to the percentile confidence interval we used earlier. Another possibility is to assume a student T distribution. That's easy to do. You see, it gives quite different numbers, a lower endpoint of 89 as opposed to 95 from the Bootstrap approach. And in this case, I would say this distribution is so skewed that the Bootstrap approach is unquestionably superior to the student T approach. Can we do a simulation? Well, I suppose we can by assuming that the observed data are the entire population. So we'll do a simulation of 10,000 tries where we draw a sample of n arsenic measurements with replacement, compute t star, and get a confidence interval from these results, getting L, getting U, and we will count 1 if the value of x bar, that is the true mean, is greater than L and less than U. In this case, we can say x bar is the true mean because we're assuming the sample is the population. We'll also check times when our lower limit was wrong because it was in fact greater than x bar, or when our upper limit was wrong because it came out less than x bar. Let's display what goes on for the first 100 tries and look at the results. So, as usual, the red is our sample. The vertical line extends from the value of L to the value of U, and you can see that the red line is very definitely not always in the middle of that bar. That's because our data are skewed and that information has been captured by the Bootstrap. Here's a vertical line at the true mean. What fraction of the time did we capture the true mean? 95.3%. That's pretty good. It's a 95% confidence interval. And now for the real test. This data is wildly skewed, but in spite of that, we were off on one side 0.2 2.49% of the time, and off on the other side 2.21% of the time. So not only did we get a good 95% confidence interval, we constructed one that missed with equal frequency on either side. You've already seen that blindly using student T would have given quite a different confidence interval, and that confidence interval would not have passed this test. And we are done.